First of all, thanks for coming. I know most of you are stuck here because your flights are tomorrow, and the people who could leave took the train home. But I'm just joking. Thank you very much for coming to this talk, Resilient Predictive Data Pipelines. Just to get a show of hands, how many of you actually work on data pipelines? OK, so looks like 10%, not bad. So a little bit about me. I work at a small software startup in San Mateo called Agari. And before, let's say about a year ago, I worked at LinkedIn, Netflix, eBay, and Etsy. And at those companies, I work in roles mostly dealing with scaling and scaling of data. I'm also a co-chair for QCon San Francisco. And in my spare time, I am a committer on a newly incubating project called Airflow, Apache Airflow. And I also report to a little teenager and his mom in that picture below. So you might be asking yourself, why is a data pipeline talk in this always availability or always available track? So mostly, always on work has traditionally focused on the availability of serving systems. And serving systems are typically synchronous or semi-synchronous. By semi-synchronous, I mean there's some sort of asynchronous aspect to it, but it's usually time-bound. They're often transactional, and they're most often latency sensitive. And why is that? Why have these tracks not represented more of the data pipeline community? And it's mostly because outages are big news, right? In 2007, it was a little bit of a badge of honor around that time in the Bay Area for your site to go down, because it meant that you had the thinking was that you had a lot of traffic and your site went down. And I think even one of the pitches that AWS made at the time was, you're a startup, you can't afford all this infrastructure just for being on TechCrunch's front page for 2 days. So use EC2 to scale up. And the reality was, in 2007, 2008, 2009, a lot of sites that are stable today were not so stable back then. And they actually thought about their down page. They redesigned it many times to have the coolest my site is down page. And the problem with that is, after a while, your site being down actually becomes your brand. And for the first 3 years of Twitter, people really recognized the fail whale. And how many of you have used Etsy? Raise your hand if you have or heard of it. OK, so does anyone recognize who this is? Raise your hand if you recognize. No? So he's one of the founders. His name is Haim, and he was the DBA / sysadmin for Etsy, and Etsy was going down quite a lot around 2007. And then it became a cultural movement in the community of makers to craft stuff about it being down. And it became one of the popular categories on Etsy. Now, as I mentioned, this track is usually about synchronous systems or semi-synchronous systems. But I would say that it's more important to most of the modern websites that we start focusing on data flow systems, because data flow systems are arguably more important to most online businesses today. And they have these features that they're asynchronous, and they're not really latency sensitive, but they are throughput sensitive. And why do I make this statement, right? So if you go to your favorite sites, right, for example, Netflix on the top left, or even Spotify, there are data pipelines that are building personalization models to predict what you like to watch or listen to and keep you engaged with the site. And in the case of things like Pandora, or actually not really Pandora, but mostly Netflix that have a subscription model, that leads to churn reduction, right? Because they don't want people leaving the site. For social networking sites like LinkedIn or Facebook, you'll often find this people you may know widget, right? And it's super important to these social networking sites to continue to grow the edge of their social network. And for example, in the case of LinkedIn, right? LinkedIn makes 60% of its money from recruiters finding you. And something like 70% of the profiles had nothing beyond the name, right? So by adding more of your friends, LinkedIn hopes to shame you a little bit into filling out your profile so that recruiters will find you, and then they can sort of get more profit from that side. So it's very important that the network grows for these sort of companies. On the upper right, you'll recognize Amazon, and the people who bought X bought Y, and people bought X and Y together. And again, lots of clicks and purchases happen through that route for Amazon. And lower down below, eBay. So 7 years ago, I actually helped build the ranking algorithm that's still the default on eBay, called Best Match. And what that essentially does is it will rank results by what's being purchased, like right now or in the last n minutes, in order to prioritize, like make it a higher probability that what you click on will actually get bought, and eBay will get a larger chunk of that profit. So all of these businesses, depend on these pipelines. And in eBay's case, it's like a live pipeline of whatever you're buying, watching, bidding on, that sort of stuff. And it's like changing the ranking order of the results on the fly. So I hope I've made the case why it's important to have an always-on data pipeline. And modern systems today, it's really architectures that provide both. Provide a serving architecture that's always on, and a data pipeline architecture that's always on. And this is sort of a design, you could say, for these systems. On the left, you've got the typical serving stack or serving architecture. You'll have front-end load balancers, followed by web servers, followed by a microservices layer. And then you'll have some sort of data layer, which is essentially databases, search engines, caching machines, graphs, all of that sort of stuff. And the one mistake I feel, it's sort of like a stumbling point that every company sort of makes, is they start hiring a couple of data scientists, and maybe you've seen this in your experience. And then the data scientists start running these expensive scan queries on the OLTP database, and it soon becomes like a problem of availability. So as like a step forward, like LinkedIn maybe 7, 8 years ago had decoupled their like OLTP database from all their analytics and product, like data product stuff. And essentially, there was a data integration layer. At that time, it was something called Databus. Now it's Kafka. Essentially, by separating these two architectures, you can keep both of them available. And that's sort of the goal of this slide. So what are some of the challenges with keeping a data pipeline up? I mean, you're probably very familiar with keeping a high availability site up, right? You avoid like single points of failure, that sort of stuff. But what do you do for data pipelines? So one of the problems is called the blast radius problem. So let's say you have someone in your job at work who writes some code for a data pipeline job. Let's call it job 1. And job 1 reads data A and writes data B, and say your developer introduces a bug. There's another job called job 2 that reads that data B and writes out data C. And I think you get the point. There's another job that reads that output and, input and writes another output. And finally, some output makes it to a serving system, because at the end, like LinkedIn widgets have to surface some of that data. And that's probably where you're going to catch the bug. And if it's like a recommender system, you're probably not going to catch it for a long time. I remember walking along the halls of Netflix a few years ago and ran into one of the VPs. And he said, "We found a bug." I'm like, "Great." He's like, "It's been around for 2 years." I said, "Yeah, well, that's recommender systems. There are probably many bugs you don't even know about." And essentially, the reason this is called a blast radius, right, is that a bug that was created in an upstream job corrupted data downstream, and it affected a huge swath of services. And what I showed was just one path, but in reality, there are many jobs that depend on the output of the first job, and so forth. There are many jobs that depend on the output of that line of jobs. So it's actually a whole bunch of jobs in a pyramid that are essentially affected by corrupt data at the nucleus. So why is this an acute pain point in companies like LinkedIn, Facebook, and such? Well, first of all, you've detected the bug, right? So the next step is to go about identifying the cause. So first you look in your serving database and say, OK, this data is bad. What wrote to this data? Oh, this job. Let me go and look at this job. Let me look at its code. Let me look at its input and its various inputs. And then you get into this situation. which is like awesome if you're my 3-year-old boy, but it's not so much fun for me, right? Lifting every rock and looking for the bug, and eventually, if you still have a job and your sanity, you will come to the point where you identify where the bug is, right? Yay, we found the bug. So now what do we need to do? We just need to deploy a fix. But wait, that's only going to fix data going forward, and this bug has been around for weeks. So it's probably corrupted a whole bunch of historical data, and I need to find out who to contact. So let me contact all the teams that own all of the jobs that care about this output, and then they need to do the same for everyone that uses their output. And basically, this is what you get into, right? You're herding cats. You're trying to figure out what's affected, how do you let everyone know, all of that sort of stuff. And they all run on different cadences, so it's a bit of a pain. So essentially, after all of this is done, you've rerun all of the jobs, all of your data is clean, and then the next bug comes, right? So very quickly in this field, you learn that there's a high cost in people, time, and morale. People get burned out. So what can you do about it, right? Someone will come and say, I have a great idea. Let's do more testing, right? Testing is going to solve this problem. Testing doesn't always solve this problem. Actually, in reality, it more often than not doesn't solve this problem. Because in data pipelines, bugs are either in the logic, or if you haven't changed the code for like a year, it could still break because something in the input changed. And the data is typically semi-structured or unstructured. And for you to mimic all of the ways it could possibly go bad to create a test corpus and maintain that test corpus, it's a huge investment. So a better option is more like detect that there's a problem and roll back or fix forward, like an automation solution. So what you really want is at any stage of your pipeline to be able to detect that there's a problem. That helps you essentially identify what's wrong and then fix it forward or roll it back in an automated fashion. Another problem with data pipelines has to do with timeliness. So imagine that I have these 3 jobs that I talked about before, job 1, job 2, job 3. So the output of job 1 is going to be read by job 2. The output of job 2 is going to be read by job 3, and job 3 is going to push something to a serving system. And in my definition here, a job is equal to a workflow, and these are a directed acyclic graph of tasks. Now let's say I'm going to run this on a daily schedule. So I run it on Monday, I run it on Tuesday, I run it on Wednesday, and everything looks fine. Thursday looks good too. And hey, it's Friday, it's time to head out to the bars, right? But something is not looking great because my first job is taking double the time. And then it's the weekend, you're with your family, and all of a sudden, job 1 is taking 3x the amount of time, and you're getting paged, and what was supposed to be a daily job doesn't complete in a day, you're out of SLA, and you have to go in on Sunday and fix it, because if you can't finish a day's job in a day, you're never going to catch up, right? So now you have a problem. So the question becomes, why do jobs, especially in the big data space, get slower, right? Why do they get slower? So I'm going to give you an actual example. So what you're seeing here is time, like performance of task over time. So the x-axis is about 2 months of data at hourly points. The y-axis is the task duration. The task duration is expressed here as a fraction of an hour. So we're running an hourly job in this case. So essentially what you're seeing is a large variance of one of our jobs, this one in maroon. It's actually a Spark task. And the Spark task, it's actually a Spark job or task in our DAG. It's taking up to more than half an hour to complete. So why does that happen? So it turns out in the first week of January, one of our data science folks started computing some new features. And that's perfectly acceptable, because that's what he's supposed to do. Compute some new features for some sort of prediction model. But what's not OK is over the next 4 weeks, it starts getting progressively slower. And it turns out that his model building or feature building code was looking at an increasingly growing window of data instead of like a sliding window of data. And as a result, it was doing longer and longer scans, and it was just taking longer to complete. So he fixed it. And then he made a couple other bug fixes. It took a few weeks, but we're all in good territory, and we got back down to 9 minutes. And we all took a deep breath, and they pushed new code 5 days later, and we're back to it where we were before. And essentially, there's a regression once again. And if you've worked in the web space, you would have noticed over the last few years, right, this tension between ops and developers, right, where devs are like writing code, and then ops have to maintain it and getting burnt out, and then there's like this like kind of tension between them. Well, that sort of thing is playing out in the data space. You have data scientists, these guys from like academia, like check out this new algorithm, I'm going to run it, and then the data engineers are like, why are you doing this to me? I'm like so tired out by now. So it's actually coming to a point where people are realizing this, and data science and data engineers are forming single teams of called like data science and engineering, where they can work together, because the effect of a new algorithm will be a regression, and there's actually a virtuous cycle that we should all accept. Essentially that you will compute new features, stuff will get slower. Your data size will grow, stuff will get slower. Then stop, look back, and try to like trim it, optimize, and then continue. And that's essentially the virtuous cycle in the world of big data today. And also, latency matters a bit, right? Because we're a throughput-based system, but if you can't finish your stuff in a day, you're in trouble. So given these two kind of problems I've talked about, one has to do with correctness, having a large blast radius. If you have a bug that affects correctness, it's going to affect a lot of jobs downstream, and also timeliness, right? What sort of desirable qualities or design criteria can we come up with? So we have 4: correctness, timeliness, operability, and cost. And of course, cost is something I threw in because I'm in a startup, and we have a finite amount of money. So correctness is all about like data integrity. Don't lose data, don't corrupt it, don't duplicate it. If you're doing predictive stuff, the output distribution shouldn't change too much. Timeliness we talked about. Operability is about putting in tooling that does fine-grained monitoring and alerting. We also need something like quick recoverability. And for cost, we want to build something that's pay-as-you-go. We don't want a bunch of standing infrastructure that we're paying for when we're not using it. So I'll make one point here. How many people have seen this before? Just sort of raise your hand if you've seen this specific graph or this image. No? So I actually saw this at a talk a guy from Etsy gave many, many years ago. It's about MTTR and MTBF. So MTTR is mean time to recovery. MTBF is, as you've heard in this heard today, it's mean time between failures, right? And Rolls-Royces are built slightly differently from Jeeps. So Jeeps are built to be abused, right? Their owners abuse them out of love, of course, but it's still abuse. And they break down a lot, right? But they're also super easy to fix. And they're designed that way. They're designed to be used outside of their design boundaries. A Rolls-Royce works great on the country roads and in front of a hotel. But if you take it up a hill, it's going to spend like 2 months in a shop. So the idea is, how should you build your website? Or how should you build a data pipeline? Should you build it to never fail, like have like a lot of tests to catch every possible problem that can happen? Or do you just roll with it, right? A bug happens, it's in production, you hit a button, you roll back immediately, you have all the tooling in place to recover quickly. And the point I will make is data pipelines in the past have been treated in the MTBF way. And like I personally came from the high-scale web world, I actually believe MTTR is the way to go. And if you go online, there's a YouTube video of a set of Marines taking a Jeep apart and putting it back together in 4 minutes. So it's quite impressive. So how can we use some commonly available tools, right, to meet our design goals? What are some things available to us? And available to my company is basically Amazon. So we started looking at some of the technologies. So just to get a sense of the room, how many people here use Amazon Web Services? That's excellent. How many of you, keep your hand up if you use SQS? Oh, cool. OK, very good. So it looks about like half of you actually use Amazon. So SQS, for the others, is a low latency, highly scalable, high available message queue. It's a queue, but it's not exactly FIFO. And it's pull-based. So actually, so I think I'm on this slide now, right? So here's an example to teach you sort of how it works. So imagine that you have producers, and they're producing messages, message 1 through 5 on this queue. And you have some consumers that are waiting to consume these messages. So the first thing that happens is a consumer will read a message from SQS. And as soon as it does so, SQS will make that message invisible, and it'll start a timer. Then the consumer in question will write the message or commit the contents of that message to a database. And finally, it will act the message, which will result in deleting the message and canceling the timer. And this is how it works in normal operation. Now, imagine the same scenario where a consumer reads this message, and it takes a bit of time to write the message to the database. During that time period, the timer goes off, and the message now becomes visible and available for some other consumer to read it. And so the consumer at the bottom picks it up, commits it, and acts it. So these are like the semantics of SQS. Based on this model, you can actually implement transactions quite well, because as long as your writes to the database are idempotent. And one interesting feature of SQS is this thing called dead letter queues that was mentioned earlier. A dead letter queue essentially is, so imagine I have this message 1, and there's a problem with it, and my code can't parse it. So rather than have message 1 clogging up the queue, you can configure SQS to bounce the message into a dead letter queue after n tries. And the benefit of this is that you can maintain high throughput in your queue, and you also never lose a message. And your code itself doesn't need to handle the transactional writing of this message to another place, which could have its own bugs. SQS just handles it for you. And similarly, you can have an alert enabled on that queue, so that whenever the dead alert queue has anything in it, you're paged. And then you know there's some sort of bug. You fix the bug, and then you drain the queue, and you never lost a message. Another thing that we use is SNS. And again, a show of hands, who uses SNS here? So about 7, 8 people? Oh, maybe 10. OK, great. So SNS, and how many of you were at the Kafka talk, Neha's Kafka talk yesterday? OK, so this is similar to Kafka, except it's push-based. It's also a topic, but it's push-based rather than pull-based. So benefits of this are when you publish to SNS, it will reliably send it to all consumers, unlike SQS. SQS will only send it to one consumer. But the downside is it will make some number of attempts to send it, and if it can't, the message is lost. So is there a way we can leverage this beautiful transactional multi-push feature with what SQS had, which is the ability to reliably save and write data? And there is. Am I off by one slide? I think I actually am off by one slide. All right. So this is actually the pattern that we have. The idea is basically that you have a topic. And the topic, in this case, is an SNS topic. And you have 2 messages in it, message 1 and message 2. And you can Amazon allows you to register 2 different SQS queues, or multiple SQS queues, as subscribers to a SNS topic. So in this case, we have 2 SQS queues subscribed to the SNS topic. And whenever we publish messages to the SNS topic, it's reliably multi-pushed to the SQS queues. Then we can have services downstream, consumers downstream of each SQS queue to reliably write the data, to read the data and commit it to a backend. To drive this home, let's say that we wanted all of our data to be written to an Elasticsearch cluster and also to our Cassandra DB. We can't really do that in a consumer in a transactional way, but one way we can do it is through this model. We have producers producing messages to SNS topics. They get pushed to each of these 2 queues. We have separate consumer groups, the purple group and the green group. The purple group is responsible for Elasticsearch updates. And the green group is responsible for Cassandra DB upgrades. And this model works really well for us. So now let's put these different sort of technologies together to build an actual fault-tolerant pipeline. But before I go there, I should give you some context about what Agari does. So first of all, we don't steal your passwords. We try to prevent others from doing so. And we've been operating in the consumer space for about 5 years. So 80% of consumer inboxes at Gmail, Hotmail, Yahoo, Office 365 are protected by some of the technology that Agari built you won't even see a phish email in most cases because it'll be filtered out by the inbox provider. We are now focusing on like solving this problem for the enterprise space. And what that means is we put these like collector like appliances in each of our enterprise customers' data centers. And every time they receive an email, they send us the headers for that email. What we do is we use a trust model to analyze the email to determine if it's phish or not. And this is not a spam problem. It's like we're looking for phish. Phish is something more malicious. And then we score the email, and then our current product shows it in a web UI. Our future product will actually be inline and eliminate such email from getting through. So let's put this together in an actual framework. This is our current batch pipeline. Later on, I'll be talking about a real-time pipeline, but this is our current batch pipeline. So what we currently have is these collectors in the wild. They're sending data to S3. Every hour or so, we create an EMR Spark cluster, which is an Elastic MapReduce Spark cluster. We spin it up. We suck in all of that data for the hour. We will score it and also generate some statistics, write it to a different S3 path. That S3 path will trigger off a series of SNS and SQS alerts or events. And we'll have what's called an autoscaler, which starts off with the size of 0, spin up, and start rapidly ingesting that data into our database so that the web UI can see it. So there's some benefits to this model. Let's first talk about how we solve the cost and timeliness problem. So what I just mentioned happens during runs. But between runs, we don't pay a dime. I mean, what we essentially have running between our hourly runs is just an S3 bucket where our customers can continue to send data. And we also have a database, a Postgres database that's sitting around. It has data from the previous runs and a web UI that hits it. And we also have one box that hosts Airflow, which I'll talk about a bit later. So let's say it's the end of the hour, and it's time for the next run. Airflow will spin up EMR, and it'll execute that whole thing where everything gets spun up just for that ingest. So this is sort of how we tackle the cost problem. What about timeliness? So I've kind of mentioned autoscaling a little bit. So again, I'm going to ask the crowd, how many people use autoscaling here? OK, 3, 4. OK, cool. So yeah, we use autoscaling. Autoscaling is essentially Amazon's solution to cluster management. Given some rules, it can scale a cluster in or out of variable size to deal with variable load. So it's typically good for feeds, like data feeds. It can also be used to just keep a cluster of fixed size up all the time. So that's another use for it. And as I mentioned, we use it for this case. So one of the challenges with using autoscaling is picking the right metric for scaling in and scaling in and out. So our first pass at this was to use CPU. We thought, let's use CPU on the importer box to tell us whether the cluster is overwhelmed and needs to be scaled out, or if it's underwhelmed and underused and should be scaled in. So that was our first pass at this. So I'll explain sort of what's happening here. So we have an orange graph, and that orange graph is throughput of messages landing in SQS, right? These are like published messages per second. And because there's nothing in the autoscale group, the green curve, which is the consumption of those messages, starts off at 0 and slowly starts ramping up. The blue curve, which is like right at the bottom, it sort of looks like a little line. That's CPU, but really think of it as a proxy for the size of the scaling group. That's essentially what it is. It's total CPU, so it's a proxy for the size of the autoscaling group. So what's happening is the autoscaling group is growing, right? It's expanding, and as it expands, the consumption rate starts increasing, and eventually it crosses the production rate of messages, because after Spark is done, essentially, at some point there's nothing left to produce, and then it catches up and drops down, right? The green curve drops down. So, and the curve at the bottom, it shows sort of like a little mesa. That's that's like the effectiveness of our auto-scaling. So what we're doing is we're using 40% CPU, average 40% CPU as the signal for scaling out. So we tell ASGs, if the CPU on average in the cluster goes above 40%, add more machines to the cluster. And when it drops below something like 10% or 5%, then start scaling in. Because we consider, I think, 5% noise. Now, this should work, right? But it doesn't. And the reason is sort of shown here. So what happens is when you get just a few messages left on the SQS queue that are now in flight and being processed, 90% of the machines are doing nothing, and their CPU drops to noise levels, and then the average drops below the 5% trigger, and then all of a sudden, AWS sends the ASG scale-in events. It says, start scaling in. But it's not smart about which 1% of the machines are currently doing stuff. It's just killing machines like this. And the machines that are actually working on the last 5 messages never complete. Essentially, there's because they're being scaled in randomly without any knowledge. So there are a couple of machines that keep trying to get the next message from SQS, and they're like, OK, I'm going to process it. And the autoscaler tells it, die, right? So we had to find sort of a better means to do scaling. And the more obvious thing to do was actually to use the queue depth. So if you remember from my earlier sort of design, the messages can be visible or they can be invisible. So what we do is we use 2 separate scaling triggers. We use a scale-out trigger based on the number of visible messages in a queue, and we use a scale-in trigger based on the number of invisible messages in the queue. So what does this mean in practice? So as messages are added to the queue, the number of visible messages grows, and we just keep growing the cluster like a balloon until there's nothing left in the visible queue message queue. And then we're at fixed size, and we just start consuming all the messages. And at that point, the orange curve, which is the number of visible messages, are all, at this point, they've all been consumed, and we're waiting to write them to the DB. Once that goes to 0, and that means there's no message left to be consumed, and we act, there's no message left to be act, it's safe to scale in. We scale the whole cluster in. And this works really well for us. So with this model, we can actually figure out both our timeliness and cost. We can actually solve those 2 design goals. I will mention one thing with EMR Spark. We can actually predict before the run how many Spark resources we need for that next run based on some metrics. So we can actually scale it out so that it doesn't run into bottlenecks. But if you want to know more about that, you can come and talk to me. How about operability and correctness? So for operability, we were essentially looking for some sort of automation that can manage all of our workflows. We wanted something that was easy to manage, easy to author. Like we want to author workflows. We wanted to get visual insight that could tell us about the state of our workflows and the performance and their performance. And we also wanted something that integrated with all our existing monitoring and alerting. So we found Apache Airflow. Actually, back then it was called Airbnb Airflow. And just very recently, it became an Apache project. So we started leveraging that. And essentially what you get is, this is not meant for you to read, but this is essentially a workflow written in Python. And essentially, you write your workflows in Python. Before this, at like LinkedIn, we use Azkaban, which was essentially a zip file of a bunch of conf files, config files. And Uzi, which was used heavily at Yahoo, was like a gigantic XML file. And those are horrible things to deal with. And a few years ago, Spotify came up with something called Luigi, which is also based on Python, but the UI was not very good. And it was also not very stable. So when I saw this pop up about a year ago, I was like very excited. And then when your code is parsed, it'll actually show you the graph, the DAG, the workflow for it. And the workflow on the left is actually used to manage the whole pipeline on the right. And you can manage multiple DAGs very easily. We have something like 10. Most of them are model building. And you can see for any given run what the slow parts of it are, right? You don't need to dig into it. It shows you. And in this case, it tells us a given run took 20 minutes. And the slowest part was the Spark job that took like 10 minutes. And you can also see, as we saw before, a historical trending for all of the tasks in a given DAG, in a given workflow. On the alerting side, we use we use a combination of PagerDuty and VictorOps. Both solve the same problem. If there's an issue on the site, it'll page the first on-call and try a couple times, and then start escalating to follow-on on-calls. It integrates well with Airflow. So we get certain types of alarms, like if the workflow is slow, it misses its SLA, or it's encountering data loss. And when it does that, it'll page us. And more interestingly, we integrated it with Slack. What you see here is Airflow telling Slack that you've missed your time SLA, you missed your time SLA. And then further down, it says, hey, this run finished, but it lost data. And there's a link in it. You click on it, and the link will take you right to Airflow and show you, hey, there's a data loss that's happening right now. And it works really well. So with this combination, we're sort of able to hit all our targets. That's sort of our batch pipeline. The next sort of thing that we're working on is our stream processing pipeline. So this must look kind of overwhelming. I mean, it's actually funny to have like the title that says architecture, and then show something like I threw up on this slide. And depending on how old your kids are, you may recognize like Richard Scarry's like BusyTown, and basically it looks like a BusyTown design. But there is some, there's something to this madness, and actually it's a pattern. And the pattern is that we essentially have auto-scale compute followed by kinesis, which is sort of like Kafka. So anything that does compute will read from a kinesis stream, do some compute on it, and it'll be auto-scaled so that it's scaled for compute. And then it'll publish its data downstream to kinesis. And then something on the other side of kinesis will read it and do the same. So essentially, everything is built of this repeatable pattern of compute with kinesis in between, and the compute is auto-scaled. And we call this elastic stream processing, essentially, because kinesis and the compute can be elastically scaled. And I'll talk about that a little later on. And then there's this other thing on top called a Schema Registry. So how many of you have heard of a Schema Registry before? Especially if you've used Kafka, you would know about this. Awesome. All right. So I'm going to talk a little bit about Avro. How many of you know either Avro or Protobuf or Thrift? Awesome. OK, so a lot of you. So we use Avro. So just like you have data in a database, right, and that data is protected by a schema and some sort of schema enforcement, what about data in files or data on streams? That should also be protected by some sort of schema. And Avro provides, so do the others, it provides types, cardinality, optionality, and also does nesting, which is even better than most databases do. And it also supports this very cool thing called schema evolution. So in our case, we have 10 customers that all have different versions of our collector. They all upgraded at different times. And they're all sending slightly different schemas to us. Like the data is coming in binary, but with slightly different schemas. And then we're pushing code on our readers, like at will. And one of the best practices is this decoupling model, right? So we have queues to decouple, but then they would be coupled by schema, and we want to decouple that even further. So data coming in we use this concept called schema resolution, which will take a reader and writer schema and figure out what's common between them to be able to read any input that we get. So this is kind of an example of Avro. OK, did you guys not see that? All right. So this is an example of Avro. So it's a self-describing schema serialization format. And as I mentioned, it has types and nesting. Now, typically, when you're working in sort of Hadoop, you store the schema that the data was written with the file. And that's because the data files are so large, the schema overhead is like tiny. But in the world of streaming, the overhead is like 99% of the data you're sending. So it's not a good idea to send the writer schema appended on the top of the actual data packet that's being sent. So instead, the thing that LinkedIn came up with many years ago was to strip out the schema, send the payload without a schema, but just an identifier, and then on the consumer side, to look up the schema, use that to decode the binary. And the only problem with that is it's very tightly coupled to the Kafka project. So what we did is twofold. We decoupled it from the Kafka project, And we also made it like something that works perfectly well in the cloud. And essentially, we're going to open source it in a few weeks. It's basically a Gradle script that you can use to publish a zip file which has 2 Lambda functions in it. And the Lambda functions either take a register schema call or a get schema by ID call. And whenever you call the register schema call, it will validate your schema to make sure it's backward and forward compatible, both as a reader and writer schema before it accepts it. And you also pass it on the fly in the URL, a JDBC connection URL, a URI to the database that's backing it. And on every call, you can change it if you wish. But so for example, you can pass it a JDBC URL to Dynamo on that call, and what it will do is it'll validate it. If it works, it'll register it at that URL and then return success to you. And it'll return an ID to you, and then that ID you pass down the stream, and the consumer will read it and look it up and be able to decode on the fly. So we'll be open sourcing this in a few weeks. And of course, for those of you who have not used Lambda, it's basically the next evolution of serverless. It's essentially the next evolution of autoscaling. You're given a hosted execution environment. All you need to do is upload zip in Python, Node, Java, now I think Ruby. And then when you upload it, all you do is you pick sort of a profile like medium memory, medium CPU, high CPU, super high CPU, and 256 gig RAM or 1 terabyte RAM or whatever. I don't exactly know how large it gets. And then as soon as you do that, you get a new version. And the beauty of this thing is if you have a bug and you want to roll back, all you do is in the UI, you say $latest equals v1, and you've just rolled back your code, your bad code. So it's actually a very useful innovation. And I think I'm going a little bit over time, but I'll just mention this. We're also creating a tool for elastic stream processing. Currently, if you use Kafka or Kinesis, your scalability is per shard. If you have 3 shards, you have an exact provision limit. What happens if your producer starts producing more data? So what we do is we will detect that there's such a problem and automatically add new shards and auto-scale the compute to handle it, and then detect when it's below provisioning and do the opposite. And this also uses Dynamo behind the scenes, so it'll also automatically scale Dynamo up to the next provision limit and scale it down. Both of these will be open source if you guys want to follow it. Feel free to follow these 2 Twitter IDs. And I guess there's really probably no time for questions, but if you have any. Oh, we have 5 minutes for questions.
There is one question from the app, and it is, what was the VP's response when you told him there were many bugs in the recommendation system?
No, so I didn't tell him. I was from the infrastructure team at Netflix, and it was actually the recommendations team who told me. And I think there was some frustration. But I've worked in recommendations for a long time, and the beauty is you never get bugs. And if you want a good work-life balance, I would work in recommender systems.
One more question. Remember to vote. I can say that while I walk down here.
It's okay. Can you go back to the slide that shows the Twitter feeds to follow? I think it's the second to last.
Second to last? Oh, the Twitter, yeah, sure. Here, sorry.
Yeah, thank you.
Right. Any other comments of the slides you want to see, or are there any questions? OK, great.
So I had a brief moment of terror when you showed the using the queue offset and lag to drive auto-scaling groups. And wondering what means you have to prevent, say, a totally stalled queue from just creating servers ad infinitum. Are you watching it? Are you setting hard caps? Do you have stall detection or some combination?
So if I understand your question, when we move to the queue-based autoscaling, you're saying how do we keep so with autoscaling, you provide a min and max size. So we take steps. So every 5 minutes, we check a rule, and the rule is the visible message depth still greater than 0? Yes, step by 4. So we take steps of 4 up to 40 or something, and we're capped at 40. And then we scale in after. We keep them all around. until the last message drops off the in-flight queue, and then we're safe to bring it in. And we love SQS and SNS, but we couldn't really use it for stream processing because it'll never stop, right? Messages never stop, and there's never a scale in. You kind of would never scale in, but it's definitely got some benefits over Kinesis. Good question. Yeah.
Right. No more questions. I think we should call it a conference, and thank you one more time, Sid.
Thank you. And
Thanks
if you have
for
questions,
coming.
come up.